Hugging Face is the central nervous system of the OpenAI ecosystem. It routes millions of models to servers worldwide every day. By early 2026, the platform tracked 13 million active users, downloading from a repository of over 2 million public AI models. The tech sector depends heavily on this infrastructure. With a $4.5 billion valuation and backing from giants like Salesforce, Google, and NVIDIA, it acts as the primary distribution channel for modern software. Security firm JFrog found that Hugging Face published 1.4 million new models in 2025 alone. That makes it the second largest software registry on the internet, trailing only Docker Hub. The massive volume of incoming artifacts has a direct consequence. Attackers are compressing a decade of traditional software supply chain tactics, like typo squatting and dependency confusion, into the AI space in a matter of months. These attacks are escalating quickly. JFrog identified nearly 500 actively malicious models on the platform, carrying hidden payloads, ranging from reverse shells to credential harvesting tools. Those individual malicious files eventually triggered platform-level incidents. In April 2024, researchers from Wiz uploaded a malicious model that successfully hijacked Hugging Face's shared inference infrastructure. Today, Hugging Face functions as essential enterprise infrastructure currently facing a steady drumbeat of targeted attacks. The underlying cause of these vulnerabilities is a deliberate design choice, rather than a traditional coding error. It stems from PyTorch, the industry-standard AI framework, relying on PyTorch's native pickle module to save and share model weights. Many engineering teams download a .pt model file and treat it like a static image or a basic text document, assuming it contains inert data. Due to the architecture of Python serialization, loading a pickle file is functionally identical to executing an untrusted binary. Until developers understand that loading an AI model is an act of dynamic code execution, their enterprise environments remain completely exposed. Serialization converts neural network weights into shareable files. The left side is secure. Safety tensors acts as a static dictionary read directly into memory. But a pickle file operates as a sequence of opcodes for a virtual machine, carrying executable bytecode alongside model data. The critical attack vector is a Python method called __reduce_, which gives the virtual machine explicit reconstruction instructions. An attacker can craft a malicious __reduce_ method, forcing the virtual machine to return an OS-level command instead of a math tensor. This malicious command fires the exact microsecond the developer types torch.load. The payload executes before a single actual tensor or weight is ever read by the system. There is no buffer overflow required here. Attackers bypass perimeter defenses by utilizing a standard Python language feature working exactly as designed. To block these payloads, platforms typically rely on static scanning tools like PickleScan and ClamAV. These scanners parse the bytecode and look for a hard-coded blacklist of dangerous imports, flatting functions like eval or os.system. Static scanners read files sequentially, halting at format errors. Attackers exploit this by compressing PyTorch pickles with 7z. The scanner hits the 7z block, logging it as safe, but the PyTorch interpreter dynamically unpacks opcodes, bypassing the shell to execute the hidden payload. This discrepancy is highly exploitable. In 2025, JFrog discovered 3 critical CVSS 9.30 days bypassing PickleScan. 10 day CVE 2025-10156 used intentional zip CRC corruption. The corrupted values crashed PickleScan, granting the payload a free pass into the active execution environment. Relying on static blacklists to police dynamic interpreters leaves pipelines exposed to continuous novel format tricks. When these code execution payloads slip through local developer defenses, they detonate inside connected cloud infrastructure. In April 2024, researchers from Wiz uploaded a malicious pickle model directly to Hugging Face's shared inference API. The payload executed on load, escaped its isolated container, and gained cross-tenant access to other customers' private models on the same server. By July 2026, attackers evolved to target automated dataset processing pipelines, utilizing an autonomous AI agent to harvest credentials over a single weekend. Beyond code execution, organizations face a silent threat vector that bypasses scanning entirely: behavioral data poisoning. A 2025 study investigated backdoor implantation in training datasets. Researchers proved just 250 maliciously crafted documents can permanently implant a backdoor into a 13 billion parameter model, forcing it to output gibberish when triggered. The attack surface has expanded. Threat actors are weaponizing both the platform's shared compute environments and the mathematical logic of the models themselves. Organizations cannot simply block Hugging Face without falling entirely behind in OpenAI development. Surviving this threat landscape requires a structural shift in how models are ingested. The vulnerable approach streams .pt pickle models directly from the public hub into production infrastructure. The first rule of a secure pipeline is an absolute ban on PyTorch pickle formats. The Safe Tensors format replaces it. Safe Tensors physically separates the raw tensor data from a strict JSON header, completely eliminating the code execution vector upon loading. Second, stop relying on floating tags, as attackers can force push malicious replacements overnight. Instead, pin every model reference using immutable commit hashes. Finally, load all external models strictly in isolated, egress-restricted sandboxes. If a reverse shell fires, it hits a dead end. AI models function as high-risk, executable software artifacts. They require the same rigorous supply chain hygiene and containment as any other critical system dependency.